This is, I guess, lecture 25 or 24. And again, I want to do an application, which is the least square method. But to do this, we need some preparation and won't be able to do it today. Instead, what we will do today is a little discussion of orthogonal subspaces. So what are these? Now, we know what do we mean by two orthogonal vectors. If V and W have zero scalar product, you can write it this way or write it this way, then they are called orthogonal. This is just a reminder. And we know that if now in today, we know that we can define different kinds of scalar products depending on what space we are considering. So today, I will only consider the column spaces, Rn spaces of arbitrary dimensions, but things consisting of things like this, column vectors, and the scalar product would be the standard one, which is that V dot W is V1 W1 plus V2 W2, just the product of corresponding components. And just a reminder that this thing I can write as V transpose times W, because V transpose will give me V1, V2, Vn, and W transpose gives me this guy, and just the rule of matrix multiplication then gives me this number via matrix multiplication. Now, so that means this orthogonality, I can write it as this. If there's zero, this implies V, and we can give a symbol. V is perpendicular to W. Like if I make it geometrically, there's an angle of 90 degrees between them. If this is V, this is W, and so on. Now, what is the idea of orthogonal subspaces? These are two orthogonal vectors. But then what are the orthogonal subspaces? Suppose if I consider some subspace, and since the best I can do is draw a three-dimensional space, so I'll give examples from a three-dimensional vector space. So you have this three-dimensional vector space R3, and over here I consider some two-dimensional, some subspace. So for example, I can consider this space spanned by the unit vector I and j, vectors of this type. then I have a one-dimensional space spanned by k vectors of this type, then every vector in this subspace, which is the subspace of this plane, this shaded plane, every vector here, this one, this one, this one, or this one, doesn't matter, or this one, is perpendicular to every vector which is a span of k. Anyone, this is just a one-dimensional space, but I take any vector here, the vectors in this shaded plane are all perpendicular to that because there's an angle of 90 degree. So then both of them are subspaces. I can call this space, let me give it a name W, and let's give it a name, uh, let's call it W1 and let's call it W2. Since every vector in W1 is perpendicular to every vector in W2, so we can say that these two subspaces are orthogonal to each other. I can give you another example. In R3, again, I can consider this space, this one-dimensional space, all the vectors of this type, and consider all the vectors of this type along this line. Then every vector here is perpendicular to every vector here. So this space generated by I is perpendicular to the space spanned by J. So span of I is perpendicular to span of J. So that's the idea, that if you have two subspaces, spaces, let's say X and Y of a vector space V, which for me today is Rn, are orthogonal. This is just a definition, and I'll write it through this symbol, that X is orthogonal to Y. Two subspaces X and Y of a vector space are orthogonal if every vector in X is orthogonal to every vector in Y. That is X dot Y or 0, or in other symbols, X transpose Y is 0. For all X belonging to this space and for all Y belonging to the other space. So we can take, for example, some example. So if I take this space, where did it go? Okay. So if I take this space, for example, A0, B0, all vectors of this type, consider the space X. All vectors of this type, where A, B are arbitrary, and Y are all vectors of this type where C, D are arbitrary, then both X and Y are subspaces of R4. And if I pick any arbitrary vector from X and Y, and I check, for example, I take this arbitrary vector from X and make the scalar product with an arbitrary vector of Y, I get A times 0 plus 0 times C plus B times 0 plus 0 times D, so I get a 0. So any arbitrary vector of X is orthogonal to any arbitrary vector of Y. That means these two subspaces are orthogonal. I can give you an example. Let me first give you a geometric example of two subspaces which are not orthogonal. So if I consider this plane and I consider this plane, so XY plane, this is x-axis, this is y-axis, this is z-axis, XY plane, and YZ plane. Then they are not orthogonal, because if I consider a vector here, this one, and a vector here, the angle between them is not 90. So I don't expect them to have a zero product. And I know that vectors in the xy plane are of this type, and vectors in yz plane are of this type. So if I make a scalar product of an arbitrary vector from one and the other, I get 0 plus BC plus 0. So in general, this is not 0. So that shows that these spaces, these two spaces are not orthogonal. Now I can talk about, so geometrically speaking, as I said, that this idea of using geometry to discover theorems is very powerful. So if I look over here and think about this example, that I have this subspace, xy plane, and I have this subspace, the z-axis. They are orthogonal, and this guy is actually all the vectors here. This subspace, which is z-axis, is a complement, an orthogonal complement to the xy plane, because this contains all the vectors which are orthogonal to xy plane. So if I consider this xy plane, it actually goes all along. Then all the vectors which are perpendicular to this plane, they are all along the z-axis. So I can then talk about orthogonal complement. So what is that? Set of all vectors that are orthogonal to a given subspace. So this set given subspace, let's say X, set of all vectors that are orthogonal to given subspace X is called the orthogonal component, the orthogonal complement of X, and is denoted by X perpendicular. So it just means when you put this symbol over here, it just means that I'm considering all vectors, the set of all vectors which are perpendicular to every vector in X. So this means that every y belonging to X perpendicular is orthogonal to every X belonging to X. That is, y dot X is 0 for all y belonging to X complement and all X belonging to X. I have already given you one example over here, and we can take, for example, this example. If I consider this, the space spanned by this, span of this is a space which is a arbitrary, it's a subspace. It is a one-dimensional subspace of R3. And if I want to find all vectors that are orthogonal to every vector, so this is X. So what would those be? I can just assume that they have some form. Let's say X, Y, Z. And their scalar product is 0 with this. So I get X times A plus Y times 0 plus Z times 0 has to be 0. Now this is already becoming 0. So all I get, A is not 0 because A is an arbitrary number which appears here. So this means X must be 0 and Y and Z are free. They can be anything. So that means all vectors of this form where Y and Z are arbitrary, all vectors of this form are the orthogonal complement of this space. It's pretty intuitive. Because what's happening, you consider this space, and if you want to consider all vectors which are perpendicular to it, they obviously lie in the plane YZ plane. You consider anything here is making an angle of 90 with the x-axis. Now you can say something very obvious about this orthogonal complement. That the orthogonal complement, like from here, we saw that this was our starting space, then the orthogonal complement is also a subspace. It turned out to be a plane. And we know that when we have a 0, 1, 0 in one place, not any other fixed number, then this is a subspace. Similarly, it happened over here that if I consider this plane as my starting space, then the orthogonal complement, which was this space, one-dimensional, also turned out to be a subspace. So this is a general property. Orthogonal complement of a subspace is also a subspace. How do you prove it? It's very simple. You can take, so suppose x x is an arbitrary vector belonging to x. Consider y1 and y2 belonging to the orthogonal complement of x. What would this mean? This implies y1 scalar product with x is 0 and y2 scalar product with x, which I'm writing to a transpose, is 0 because they both belong to the orthogonal complement. So every vector in the orthogonal complement has a 0 scalar product with the vectors in x. So to check if this guy is a subspace, you have to check the usual thing. Make a linear combination, arbitrary linear combination of two arbitrary vectors. Y1 and y2 are just arbitrary, they are nothing special. Any ones you picked. And then you make a dot product, a scalar product with an arbitrary vector of x. Using the scalar product properties, this works. And they both are 0. So that means this vector, since this vector has a 0 scalar product with an arbitrary, with any vector of, because x was an arbitrary vector, with any vector of x, this implies this has to be in the orthogonal complement, because orthogonal complement by definition contained all vectors. Orthogonal complement has all vectors that have 0 scalar product with the vectors in x. So this means this vector belongs to the orthogonal complement. So that shows, that's the thing you check. You make a linear combination, if it's back in the set, then that set is a subspace. So that means orthogonal complement is also a subspace. And there's also another very nice, along with this thing, that when we break up, take some subspace, I'm drawing the pictures for 3 dimensions, but it is kind of working in all dimensions. So like, for example, if I were in 4 dimensions and I pick a 2-dimensional subspace, like a plane like that, then the orthogonal complement will also turn out to be 2-dimensional. We will see it very soon. So it won't be just a line, but there will be an orthogonal complement. So they kind of fit together, and how they fit, we're just going to see very soon. But the another property over here is that if X and Y are orthogonal subspaces, then they have nothing in common. No vector in common except the zero vector. Because zero vector is in all subspaces, they are subspaces, so zero vector will be there. So that means that is X intersection Y is exactly zero vector. There's nothing else. So this is also kind of obvious, not obvious, this is also contained in our pictures. If I take this, consider the orthogonal complement, these vectors, then these vectors are not lying in this plane. Anything in this plane will not have a zero scalar product with itself. So the only thing in common is this point. And you can very easily see it in many, many ways. For example, how to see it? How to see it? For example, you can say that suppose a vector V belongs to the intersection, it's in both of them. This means V belongs to X and V belongs to Y. And since every vector in X is perpendicular to every vector in Y, this means V transpose V is zero. But we know that a vector is not orthogonal to itself. It's only possible when V is zero, because this means V1 times V1 plus V2, V2, Vn is zero. So V1 square plus V2 square plus Vn square is zero. So the norm is zero. This is only possible if all of these guys, because they are positive number, because they are all being squared, they are all zero. They have to be zero. So that means V is the zero vector. So the only common vector is the zero vector. Now, uh, you can do another, just from this geometry, I can tell you another property. It's a theorem. So if you consider a space, a subspace S and its orthogonal complement as orthogonal, then dimension of S plus dimension of S, this would be n, where n is the dimension of original space. So again, we saw it that in R3, if I consider this space, its dimension is 2. Then the orthogonal complement has dimension 1. And in that example, which I did, so for example, let me take another example. Let's consider this space. In R5, A, B, C are arbitrary. And I want to see what is the orthogonal complement. Well, I consider an arbitrary vector and I demand that I'm looking for all those vectors in R5 which are perpendicular to all the vectors in S. So all I have to do is check the scalar product. So this gives me A times x1 plus B times x2 plus 0 plus 0 plus C times x5 is 0. So this would be true for any value because I need it to be orthogonal to any vector living in over here. For any value of A, B, and C, if x1, x2, and x5 are 0, that is, the orthogonal complement has vectors of this kind. Where this x3 and x4 are arbitrary. So this is obviously two-dimensional subspace, and this was, the starting space was three-dimensional subspace. So again, 3 plus 2 is 5, which is the dimension of the original subspace, original space whose subspaces these are, and where you have defined your scalar product. So I'll leave the proof of it. Let's not prove it. Proof left as an exercise. And let's define another concept. So suppose let's see. Suppose U and V are subspaces of a space W. No, this is not a definition, this is another theorem. Or I could have put it as part of the previous theorem. Suppose U and V are subspaces, not subspaces. U, well, let's not write it like this. So I have told you that if S is a subspace, then so is S orthogonal complement. And dimension of S plus dimension of S orthogonal is equal to n, the total dimension of the original space. But not only that, the bases also match. If V1, V2 up to Vm, so suppose S is m dimensional, is the basis of S, and similarly we are given some basis of S orthogonal, Vm plus 1, Vm plus 2, it will go up to Vn, because we know that the total dimension has to turn out to be n. So you have m over here, m vectors in this basis, and n minus m vectors in this basis. Then if I just add these together, if I collect them together, then this is a basis for the full space. Full space V of which they are subspaces. So that means these vectors among themselves are linearly independent. This is guaranteed to me. And this is kind of obvious from what we had done before, that if they are orthogonal to each other, then they are linearly independent. They have to be linearly independent. They have no other choice. So using these properties, what we can do something like this. Stitching together orthogonal subspaces. So if I have, again, let me take help of this picture. This subspace and this subspace. So the basis of this and the basis of this is giving me a basis of the full space. So I can add these bases together over here and then I can then span my full space. So this thing is technically said in the following manner. Basically what you are saying, that any vector in this space, so because we know that any vector, what form it would take? It would be this vector, and I know that vectors over here are of this form, but if I add these arbitrary vectors like this, these are already all the vectors in my complete space. So that means you can get an arbitrary vector of your full space by adding vectors from a subspace and the vectors from its orthogonal complement. So this is called making a direct sum. So what's a direct sum? If U and V are two subspaces, so far I'm not talking about any orthogonality of a space W, and each vector in your space can be written uniquely, This is important. As a sum U plus V, where U comes from this space U and V comes from this space, the other subspace V, then W is said to be a direct product, a direct sum space of U and V. So essentially you have stitched together this plane and knitted it with a extra line, given it another extra dimension. Started with a two-dimensional space and gave it one more dimension to make a three-dimensional space. And written as W is U direct sum V. Direct sum. Now, the claim over here, claim is S and S plus S orthogonal, their direct sum is the full space V. So, well, V I'm taking to be Rn. Let's write it for this kind of space Rn. So S is a subspace of Rn. I construct another subspace by hand, which is just the orthogonal complement of S in the Rn, like again this space and its orthogonal complement. Then Rn would have this kind of structure, direct product structure. It's just fancy way of saying that you can write any vector here as a vector coming from here plus a vector coming from here, where this belongs to this space and this belongs to this space. This is very easy to see because we already said that if I take the basis of the vectors in S and add to it the vectors in the basis of S orthogonal, then this gives me the full basis. So if I have any vector for any V belonging to Rn, I can write V as A1 V1 plus A2 V2 plus AN VM, where this much is the basis of S plus AM plus 1 VM plus 1 up to AN. I'm guaranteed that I will be able to write any vector like this because all these vectors up to n form a basis of Rn. But if I stop over here, this is a basis of S, so this belongs to S. And this is a basis for S perpendicular, so this belongs to S perpendicular. So that means this vector is written as a sum of one vector coming from S and one vector coming from S perpendicular. So it would be a direct sum if I could show that this is a unique expression. I cannot write in another way. So suppose V can be written as S1 plus, well, let's write it as U plus X, where U belongs to, I know that I should be able to write it like this, where U belong to S and X belongs to the orthogonal complement. And also because I can choose many bases in S and S perpendicular. So I might think that this V, maybe I can also split it up in some other way, like this, W plus Y, where W belongs to S and Y belongs to S orthogonal. But that means U plus X is W plus Y, and U minus W is Y minus X. But both U and W belong to S, so their linear combination also belongs to S. And this guy belongs to, Y belongs to S complement, and X belongs to S complement, so their linear combination also belongs to S complement. So this vector V, which can be expressed as both of them, belongs to this W, which is also written as Y minus X, belongs to both S and S complement. But we know, we just proved that that is only possible if the only thing they have in common is zero vector. So that means U is W and Y is X, because S, the only common thing is zero. So that means it's a unique, you have a unique splitting of your space. If you are given a big space, you can split it into subspaces, each orthogonal to each other. Actually, you can think of the basis vectors as one-dimensional orthogonal spaces. So you are splitting these into, first you split off one-dimensional space, you're left with, if I start with the three-dimensional space, I split off one-dimensional space, then the rest, the orthogonal complement would be two-dimensional. Then I again split off one, the orthogonal complement will be one-dimensional. And they will all be orthogonal, they will keep being orthogonal to each other, because that's how I did it in steps, and I will be left with what we had studied before, an orthogonal basis. And you can do it, like for example, to an n-dimensional space. Split off, consider one-dimensional space, then its orthogonal complement would be n minus 1, and they will be orthogonal. Every vector here is orthogonal to here. Then you split it off into another one-dimensional and an n minus 2-dimensional, again like that, keep going. So they all, in the end, you are left with one-dimensional and one-dimensional spaces, which are all orthogonal to each other. But the most interesting application, well, not the most interesting application, but one application which we are going to use is the following. This is called fundamental subspaces theorem. But first, let's see what fundamental subspaces, we had studied them. But let's just recall some of the fundamental subspaces of a matrix. Uh, so if I consider the if I consider an M by N matrix, and I consider this kind of an equation. So since A is M by N, that means X is N by 1. So that means X is a N column vector. But the result would be M by 1. So that means B is a M column vector. Then I can consider this equation. And if I write the left-hand side, I can write the left-hand side like this. This matrix A, I can write as a bunch of columns, since it has n columns. So it will be composed of some n column vectors, which you are multiplying with this x. And we know that this rule of matrix multiplication tells me that this can be written as this. Multiply each column with these components of x. So what is this giving you? This is just a linear combination of columns of A. So, and we know, and we want to put it equal to some B. That I don't need to write as in components some B. So that means B is a linear combination of columns of A. So we have, so then we have is that B is a solution. If so, no, I should say that if I choose any B, then this equation will be satisfied. Will be satisfied if and only if B, what you say, is in the column space of A. Because what is the column space of A? It's just the space spanned by the column vectors of A. So the linear combinations of A. So that means this equation will be satisfied if it's obvious if B is a linear combination of A, And if B is a linear combination of A, then the equation will be satisfied. So it's an if and only if statement. Now, but I can also think of this equation as a linear operator. Linear operator which acts on Rn, because X lives in Rn, and takes you to Rm. We have studied linear operators. They are represented by matrices. So this matrix A is a linear operator which acts on Rn and takes you to Rm. So what it's saying is that the range, we had studied this concept as well, the range of A, all possible values of A for any arbitrary X is such that these B's which are belonging to M must be such that B solve this equation for some X belonging to Rn, but that's only possible if this is the column space of A. This will be equal to column space of A because you are now considering all possible X for any X if this is solved. So that would mean that you are making all linear combinations here to generate possible B's. All linear combinations here to generate one possible B. So that would be the range of A. But this is just the column space of A. This is just another name for the column space of A. Now, I can also consider R of AT. What happens if I consider R of AT? Now, I have flipped the rows with the columns. So AT is a n by m. So it goes from Rm to Rn. So you're solving some equation. This is acting on some vector x to give you some vector y. So all possible values of y belonging to Rn such that y is A transpose times x for some x belonging to this time Rm. And this is the column space of A transpose. Just like this was the column space of A, if I replace A by A transpose, obviously it would be the column space of A transpose. But obviously, if I consider these columns and consider their column space, which is just the linear combination of these columns, this would be same as if I take the transpose, columns are changed into the rows. So column space here will be equal to the row space here, because you're making the linear combination of same vectors. It's just that now you have put them lying down instead of standing up as columns. So essentially, the row space of A is equal to column space of AT, A transpose. Essentially, in other words, you can say that Y belongs to range of AT, or in other words, Y belongs to the column space of AT if and only if Y transpose, which is just the Y just put it into made into a row instead of a column. YT belongs to the row space because the row space has row vectors. Otherwise, they are the same. So this is the row space which we are familiar with. And we are also familiar with another kind of space, which is the null space. So what was the null space? If you have considered this equation, set of all vectors which solve it and we know that it's a space. It is a subspace. It is a subspace of Rn. Now, the claim is, this is a very interesting theorem. If A is any m by n matrix, then the null space of A is equal to the column space of A transpose and taking its orthogonal complement. The orthogonal complement of the column space of A transpose is equal to the null space of A. Let's write it in English. Null space of A is same as the orthogonal complement of the column space of A transpose. You can modify it a little bit as well. And the null space of A transpose, you can exchange the role, is equal to the column space of A and taking its orthogonal complement. So how do we see it? So if I consider this equation for the null space, consider Ax is equal to 0. I can write this A11 if I open it up. It's a m by n m rows So one way to write it is these combinations: x1, a11, plus x2 a12. Let me write it on the other side. X is on the other side. This is just the matrix multiplication. This is 0, and the next row is also 0. All these rows are 0. Ith row will give me but what is this saying? This is saying that if I pick up the ith row vector of A, which is the column vector, which is the transpose of the ith column vector of A transpose. And all I'm doing is making the scalar product with the vector x. So it's saying that the ith column vector which I can write, if I write this A as A1, A2, AN, I make not the A transpose. If I write it like this, let me denote them by B's because it's a transpose. So let's write it differently. M vectors are there because I have taken a transpose. So then each one of them has 0 scalar product with X. But if this is true, that means if I make any linear combination of them and make a scalar product with X using the properties of the scalar product, this splits up. They're all 0. But this is an arbitrary vector in the span of the columns of A transpose. So that means X is orthogonal to the column space of A transpose. But X was any arbitrary vector which satisfies Ax is equal to 0. That means the null space of A, X belonged to the null space of A. So null space of A is orthogonal to A transpose. But I haven't showed exactly this thing. This says something stronger. It doesn't only say that when I write this is true, that this is claiming that the null space of A transpose, well, not this one. Let's start with this one, not like this one. It says that the null space of A, it is true that this is saying that the null space of A is orthogonal to the column space of A transpose, but it's actually saying it contains all the vectors which are orthogonal to the column space of the A transpose. There are no other vectors. So the null space is actually the orthogonal complement of the A transpose. of the column space of A transpose. So how do we see that? So we have to prove the other way around. We have shown that if X belongs to the null space, then X is perpendicular to every Y belonging to the column space of A transpose. Now suppose let's use some. Now suppose that X belongs to the orthogonal complement of the column space of A transpose. That means it's any arbitrary vector which is perpendicular to this space. But this means X is perpendicular to all column vectors of A transpose but that implies that AX is 0 because A transpose is just this. What are the column vectors of A transpose? Column vectors of A transpose are, so the A is of this form: A11, A12, A13, A14, up to A1n. These are the rows. But when I make the AT, A transpose, then the column vectors are exactly these rows. A1n. And when I claim that A11 x1 plus A22 x2 plus up to A2n, sorry, A11 A12 x2 A1 up to A1n xn is 0. That is what means that the first column, let's call it B1, its scalar product with x is 0. But this term is generated when I take, this is again the same computation as I did before, when I take this matrix product over here. So it's telling me that if they are orthogonal to all the columns of A transpose, then this product has to be 0. That means X is, so it goes the other way around as well. X does belong to the null space of A. So that means null space of A is equal to A transpose complement. Because previously we had proved that the null space is contained in A transpose complement. Now we have proved that the complement is contained in null space. So they are equal. And now you can replace A by, if this is true for A, this is true for any matrix. M by N by M doesn't matter. So I can replace N by, this must be true for A transpose. So we have proved the other part as well. We have run out of time, can't do the example today, but we'll do the next time.